So you've probably all seen this before, right? And you've probably noticed a couple things. One, it's laid out really, really weird. And it's also full of a bunch of information that, teachers, hopefully nobody in the past has made you memorize. I am definitely not going to make you memorize this. I don't memorize it. Part of being intelligent is not memorizing things, it's knowing how to derive things. So if I can find this information, that's more important than if I can memorize it. So why is it laid out like this? Well, first of all, the periodic table was never meant to be printed on paper. It was actually made as a 3D model. It started at the top as hydrogen and it spiraled around down like a cylinder, and adding more protons as you went down. And as it went down, it started having some features to it, but they couldn't print that in the 1800s. So they had to lay it out flat, and this is kind of what they came up with. But essentially, think of it like this. So this column over here, this is what we call the S block. This over here is the P block. In the middle, we have the D block, and at the bottom, we have the F block. So it has something to do with the orbitals and the electrons that are found on the outer spaces, because again, it's those electrons in the outer space that give that element its ability to interact and how it's going to interact. The number of protons determines its properties, but how it interacts and how likely it is to bond and in what fashion is it going to bond is determined by the number of electrons that are in the outer shells. And that's what this tells us. For example, look over here on this side. Here is sodium. We said sodium has one electron in its outer shell, right? All of these in this column have one electron in its outer shell. Look on the other side. Here we have fluorine, chlorine, bromine. Chlorine, didn't we say chlorine is just missing one electron in its outer shell? Guess what? All of these are missing one electron in their outer shell. We said chlorine is extremely electronegative. It's going to take, because it's missing that one. It's kind of like the crack addict of the elemental world, because it's missing just one. All of these are missing just one. They're going to very aggressively try to take one from someplace else. When you put chlorine next to sodium, well, it strips it off, right? It strips it down, and you end up having an ionic bond. Oxygen. It's right next to fluorine. It's missing. It's not missing one in its outer shell. It's actually missing two in its outer shell. Oxygen is extremely electronegative as well, because oxygen will rip other molecules apart or other atoms apart to take their electrons. To give you an example, if you have iron that's outside, like your car, or just metal that's outside, usually iron. It usually has a waxy coating over it or an oily coating over it. But when it gets wet, that oily coating washes off. And then what happens to metal after it gets wet? It starts to rust. It forms iron oxide. Oxygen in the air is literally stripping the electrons off of the iron to get their fix, to get that two more that they need, and it's binding, causing them to bind together to form iron oxide, which is rust. So you can imagine this table is actually telling us a lot. But look at the very, very end. While these are missing one in their outer shell, these are missing two, these are missing three, these all have a full outer shell. They're stable. They don't react. They're good, right? They got a full outer shell. We call these the noble gases, and they generally don't react with much. So as you start going down and you have that S, the P, the D, and the F block, remember I said it spirals down when the original way the table was supposed to be? As it spirals down and it goes through the S's and it starts adding more, when you start hitting this first row in the D block, that spiral bumps out and it has like a lump now that it's going to go off on, and that's representing the D orbital. Well, once you get down a little bit further, you have the F. It's another bump that comes off of the D orbital. So it starts adding and showing where these electrons are. It's a great table to use. One of the videos quizzes you have is going to cover the periodic table, but I thought I'd take a moment just to kind of go through that. So now let's talk about isotopes. Isotopes are really fun. Remember, you have protons, neutrons, and electrons. You cannot change the number of protons. Electrons, we've already changed. That causes ions to form. So isotopes is when you change the number of neutrons. So what does a neutron actually do? Well, imagine you have this proton in the middle and you have an electron on the outside, and that electron is orbiting super fast, but at any one point in time, it's still pulling on the proton. That electron's negative, proton's positive, they want to connect, right? So if you were to watch it, that electron as it orbits, that proton is chasing it. And so the center of the atom, the nucleus of the atom, is actually not sitting still, it's moving, right? So if you had a bunch of protons and a bunch of electrons, you can imagine how unstable the nucleus would be as it bumps around and tries to follow those many, many different electrons. Well, that's not good. The more unstable you are, the more likely you are to fall apart. How do we stabilize it? How do we keep these protons from moving around so much? We weight them down by adding neutrons to the nucleus. So the nucleus now won't move as much, and it stabilizes the atom. So neutrons stabilize an atom, keep the electrons from pulling and protons from pulling each other apart. But what happens when we change the number of neutrons? We start messing with the stability of the atom. I'll give you an example. Carbon, which has 6 protons, therefore 6 electrons, also has 6 neutrons. And we call that isotope, that version of carbon, we call that carbon 12 because 6 protons, 6 neutrons, 6 and 6 is 12, right? And it has a stability rating of 98.9%. That's pretty daggum stable. I like that. But let's add one more neutron. So now it's 6 plus 7, 6 protons, 7 neutrons. So this is going to be carbon 13. It jumps down in stability to 1.1%. It starts becoming unstable. That's not good. We can add one more neutron to it. Now we have carbon 14. That really messes with the stability of the atom, and it has less than a 0.1% stability rating, which means it's vibrating now. It's going out of control. We've started messing up how the atom interacts, how the protons and electrons interact, and it starts becoming stable. And what happens when they become unstable? Well, they become radioactive. Those particles bump around and they hit each other and they start giving off energy in the form of radiation. It just radiates out. There's all different types and levels, alpha, beta, gamma, type of radiation. And carbon 14 is actually naturally occurring. So is carbon 13. Almost all isotopes are naturally occurring. Some are just more deadly. Something small like carbon 14, even though it's radioactive, it's not giving off deadly amounts of energy. But something large like uranium, which has a ton of electrons and tons of protons, when it starts to become unstable, there's a lot more energy it can give off. And that's more of the type of radiation we'll worry about. Like if a nuclear blast goes off, that's what you got to worry about. It's not carbon radiation. So why would this happen? What's the purpose of this? Well, as it gives off energy, sometimes we can harness that energy. Sometimes we can even track where it goes. You've probably all seen The Simpsons. Where did Homer Simpson work? He worked in a nuclear power plant, right? And they had this comic called Radiation Man, and his power was he had glowing bones. Not really a superpower, but whatever. How else do we use these? Well, there's a picture of a submarine up there, right? Simply say, well, that's a nuclear sub. That really means that it has nuclear warheads on it, but what powers a sub? Usually it's some type of isotope reaction, something that's radioactive, that's held in the core, and the energy that's being released from these highly radioactive elements, we capture that energy and we harness it and turn it into power. You probably remember a few years ago in Japan, one of the nuclear power plants kind of lost containment, and they weren't able to control the reactions anymore. You can imagine as that energy is released, it gets really hot, and so they have these giant tanks of water to cool off their reactions. Well, when they lost containment, a lot of the water became irradiated. In other words, radioactive water. Well, they dumped that into the ocean as part of their procedure to help get cool off everything, get rid of the radiated water. But it was a ton of water and a ton of steam. And the U.S. and Japan dumped this into the Pacific Ocean. Well, there's a giant current and everything, so they had to keep boats away. And the U.S. sent some ships over. A buddy of mine was actually on one of those when he went over. He was in the Navy, and now at this day and age, he's actually like late 20s, but he walks with a cane, because the radiation that he was exposed to when the ship was in that area floating around in radioactive water deteriorated the cells in his joints. So he has problems producing the correct things to help lubricate his joints. And so he has basically really bad arthritis, and at 27 years old, walks with a cane. So these things can be deadly. Isotopes can have negative effects, the energy that they release. So why in the world would we need these or be around these at all? Well, there's other things we can use them for. Remember, carbon's not really radioactive at all. Even at its isotope, it's just unstable, but it doesn't give off enough energy to really hurt us. So what can we use them for? You ever had a PET scan or heard of a PET scan in medicine? We take a radioactive element, we attach it to a biomolecule, then we inject that into your body. And depending on what we need to look for, that determines what type of molecule we attach this radioactive element to. And we call these tracers because we can then put your body into a machine that records and traces where these radioactive elements are going to and what they're sticking to. And we can record this in real time, which is great. Here's a CT scan. You can't really see where the node is on the CT scan, but when you do it with a PET scan, you can actually see where the node is. We can follow it in real time. PET scans are expensive, but if you just start off with a PET scan, then you're not having to pay the extra money to also do a CT scan that's not going to find anything. So PET scans are really cool. And I linked some information on here for you. I'm not going to go through it, but this explains what a PET scan is because you may know somebody that's had it or you may have to do one one day. Well, there you've got a link to find out what it is. And just recently, the FDA has actually approved isotopes to be made here in the US that we can actually use in PET scans. Normally we get these from other places, but nowadays we can actually make it right here at home. So how do we use it in biology? Well, have you ever seen the movie Avatar, like with the giant blue people on another planet? One of the things that the scientists were studying over there is they injected something into the nervous system of a tree, and they were able to follow that and realize that, hey, these trees are actually communicating with each other through the root system. They use a tracer, a radioactive tracer, to find it. We kind of got to do the same thing here. It's a little different, though. We take carbon-14, which is slightly radioactive. We can actually find it with a Geiger counter, and we can inject that into a plant, or we can put it in a giant bag because it's carbon dioxide essentially, and put it in a giant bag, tape that bag around a branch of a tree. The tree will absorb that carbon in photosynthesis, and then we can follow where the sugar goes. And it turns out that a lot of trees, when times are difficult, will start sharing their sugar with other trees through their interconnected roots. So we put the the radioactive carbon-14 in one tree, but we find it way down in another tree. Well, how did it get there? Well, they're sharing it, and they're sharing it in the form of sugar. Hey, you're my buddy. You're not doing so good. Let me give you some sugar. All right, let me help you live. It's a symbiotic, a relationship between them that helps them survive droughts and other times of stress that they have to go through, because it's better for all of them to do well and live than it is just for one. So, some ways that we can use isotopes. How else can we use isotopes? The other big way is through radiometric dating. This is a great one. I could talk about this all day long. I'll try not to, but radiometric dating works on a principle called half-life, right? And it's, let's say you have an atom with 100% energy, and here's 0. Halfway down would be 50% energy, so it's halfway through its life. Its energy level, rather. So if we could find where the half-life is, that we can kind of use that as a standard for time dating things. So again, 100% of its energy, 0%, 50 is halfway through. How much time passes for it to get to 50%? That's what we call the half-life. For carbon-14, it's 5,730 years. So things that are relatively newer, we can carbon date. I believe it works pretty well all the way up to about 25,000 years ago, and I believe it even sometimes it can go up to 50,000 years, but usually it's not the most accurate test. So when we're doing something like looking at fossils, and we want to know how old they are, well, we can use this radiometric dating. Now, people say, well, if carbon dating only goes back, a relatively very few years, how can we use that for telling how old dinosaurs are? Well, we don't use carbon dating as a type of radiometric dating for dating fossils. We use other types of radiometric dating, like uranium, thorium, potassium. All these things are found in rocks, and like, here's an Archaeopteryx. We want to know how old it is. We're not going to find carbon in here. It's already broken down. This thing's millions of years old, but we can find uranium, potassium, because their half-life, this version of uranium is 4,400 million years. That's 4,400 million years for the half-life. Something like samarium, 106 billion years. It's 106,000 million. That's 106 billion years. The universe isn't that old. So we have other things that we can use besides carbon to do dating. But if it's something young, like here's a woolly mammoth baby that was frozen, we can use carbon dating for it. We can back check it with it using other types of dating and make sure they all concur are relatively about the same age. But that's one way that we can use isotopes, and because they occur readily in nature. and we can use their half-life properties to for science to discover how old things are, and that's so cool.